Hi everybody. In this video we will talk about covalent compounds or covalent bonding. Covalent bonds are formed by sharing of electrons. Earlier we have learned about ionic compounds which are formed between metals and non-metals. The next topic of our discussion and bonding is covalent bonding. So the objective of this lesson will be to kind of refresh the knowledge and understanding of covalent bonding that you already have, kind of review the dot diagrams, maybe learn the dot diagrams of some polyatomic ions or some complex compounds that you have not done before, uh, identify dative or coordinate covalent bonds, and expanded octets as well as valence shell electron pair repulsion theory, shapes of molecules, metallic bonding, and all that kind of stuff. So let's start. In ionic bonding, we learned that ionic bonds are formed by the attraction, the electrostatic attraction between two oppositely charged ions. So metals lose electrons, non-metals gain electrons, and that positive and negative ions, they have electrostatic attraction that keeps them or holds them together. In case of covalent bonding, no one is willing to lose any electrons. Okay, so not usually, these compounds are formed between two nonmetals, and nonmetals have higher number of valence electrons. So nobody in nonmetals is willing to lose electrons. That's why we talk about sharing here. So a covalent bond is the attraction of two atoms to a shared pair of electrons. This is very important that we understand the concept here. And then when it comes to the test, we write it in that terminology, that it is the electrostatic attraction. No, I'm sorry. It is the attraction of two atoms to a shared pair, attraction of the atoms to a shared pair of electrons. Okay, the simplest covalent bond or covalent molecule is the hydrogen molecule. In this hydrogen molecule, we have two hydrogen atoms. Each hydrogen atom has one electron. So to make a covalent bond, these electrons will be shared. So we represent it by a line. The line means two electrons. How does the sharing happen? That the valence shell of this hydrogen atom overlaps with the valence shell of the other hydrogen atom. So you share the two electrons that are present in between. This is how a single covalent bond is formed. So this bond is called single covalent bond, and single covalent non-polar bond. Okay, but most often the covalent bonds are formed between different kind of metals, and in that case it will not be non-polar. There is a possibility of making polar covalent bonds. But right now, once again, here is H2. This is how we show the molecule. This line represents single covalent bond. Then we can talk about multiple covalent bonds. What is the scenario beside? Like for example, oxygen. Oxygen has 6 valence electrons. So if we want to draw the dot diagram or structure of O2, this is how the O2 looks like. The two electrons here share electrons, but this sharing is not complete. It does not complete their electronic arrangement. Their electronic arrangement is not complete or stable. Okay, so to get a stable electronic arrangement, that means they need to have 8 electrons around in the valence shell. They need to share another pair of electrons. Okay, so they share another pair of electrons, which was sitting at the bottom here. Now everybody has 8 electrons, 2, 4, 6, 8, 2, 4, 6, 8. Each line represents 2 electrons. So double line represents 4 electrons. So this is called double covalent bond. Double covalent bond. Same thing for the N2. I will have one nitrogen with 5 valence electrons and another nitrogen with 5 valence electrons. So to get again a stable electronic arrangement, nitrogen will end up having 3 covalent bonds. okay, between nitrogen and nitrogen atoms, all right, and that is called a triple covalent bond. So we have a single covalent bond, we have a double covalent bond, and we have a triple covalent bond, and that is the maximum number of covalent bonds that we can have: single, double, or triple. So in single covalent bond, we are sharing 2 electrons. The atoms are sharing 2 electrons. In double covalent bond, atoms are sharing 4 electrons, and here they are sharing 6 electrons. So this is what you need to understand, and you need to know why they're doing double and triple to get a stable electronic arrangement. This terminology is very important when it comes to IB chemistry, otherwise you do not get any points, if you do not use proper terminology for your questions or answers. Let's talk about the bond strength and bond length of, compare the bond strength and bond length of single, double, or triple covalent bonds. The double bonds are stronger than single covalent bonds, and the triple covalent bonds are even stronger than double covalent bonds because there are more pair of shared electrons between the two nuclei. Because there are more pairs of shared electrons. There are more pairs of shared electrons between two nuclei. I'm writing this so I want to make sure that when it comes on the test, you use the proper terminology. And triple bond, as I said, is going to be even stronger than double covalent bond. And we see the strength, we measure the strength of the covalent bonds by talking about bond enthalpies. Okay, bond enthalpy. What is bond enthalpy? Bond enthalpy is the amount of energy required to break 1 mole of covalent bond, 1 mole of bonds, and any kind of bonds. So the bond enthalpy, okay, for single, double, and triple. The bond enthalpy for single covalent bond is 348 kilojoules per mole. Bond enthalpy for double covalent bond is 612 kilojoules per mole. And bond enthalpy for triple covalent bond is 837 kilojoules. So you see, you need more and more energy to break the bonds. That is telling you that bond is getting stronger and stronger. Not only it is getting stronger, they kind of shrink because the nucleus, there are more electrons. So the atoms on the sides, they will kind of shrink. So the bond length for this one is 0.154 nanometers. Bond length here is 0.134 nanometers, and this is 0.120 nanometers. So bond is getting smaller and smaller, and since it is getting smaller, it is getting harder to break that bond. The next thing we want to talk about is the bond polarity. So bond polarity is discussed. Bond polarity is discussed based on the electronegativity. So as we know that elements on the right side of the periodic table, which are non-metals, they're more electronegative. So we are sharing the electrons between these atoms. We have learned about electronegativity. Electronegativity is the ability to attract a shared pair of electrons towards itself. The ability of an atom to attract the shared pair of electrons towards itself. If both atoms are the same, of course they have the equal ability to pull the shared pair of electrons towards itself, so the bond will be nonpolar. Okay, it's a nonpolar covalent bond. But if they have different bond electronegativities, they're different elements, then we need to see where these elements are located. We know that elements that are on the right side of the periodic table, they're much more electronegative than other elements. The smaller the size of the atom is, the more electronegative it is. So we know the atomic radius decreases as we go to the right. So smaller atoms are more electronegative. Fluorine is the most electronegative element on the periodic table. But you can get electronegativity chart in your data table. So once you have the electronegativity chart, you need to compare the electronegativity difference between the atoms. For example, hydrogen's electronegativity is 2.2, and chlorine's electronegativity is 3.2. So the difference when I do 3.2 minus 2.2, the difference is 1.0. So the common chart that we have is that if the difference is from 0 to 0.4, the bond is going to be non-polar covalent bond. Non-polar covalent bond. From 0.4 to 1.8, which is this case right here, it is going to be polar covalent bond, and above 1.8 is ionic. There are some books that tells you that from 1.8 to 2.1 it is 50% covalent, 50% ionic, and above 2.1 is 100% ionic. But your book is talking about it's even ionic that after 1.8. So atom has the power to even pull the electrons completely over to itself. So let's do another example, CCl4. So I have CCl4, carbon and chlorine bonds. So chlorine's electronegativity is, as I just said, 3.2. Chlorine is 3.2, and carbon is 2.6. So if I get the difference, okay, it is 0.6. So that means it is polar. Now, who is going to be partial negative? The one that has greater electronegativity is going to be partial negative. So I will have a partial negative sign here on each chlorine atom, okay, and partial positive on carbon atom. You do not multiply chlorine with 4 because there are 4 chlorines. So we just check one bond, that if this bond is polar or not. Okay, if this bond is polar, that means all bonds of CCl will be polar. Okay, so this is called polarity. It creates a permanent dipole in the molecule, and we'll discuss those intermolecular forces later on. But I just want to talk about polarity right here. This sign that I draw right here, that I call partial, you draw a S sign, and you can make it like this. This is a partial negative. That means it has higher electronegativity, or partial positive that has lower electronegativity. The next thing we want to talk about is the naming of covalent bonds. So let's see, how do we say naming? For covalent bonds, we use prefixes. Okay, for covalent molecules, we use prefixes. So if I have CO, I will say carbon monoxide. Okay, I hope you remember that. CO2 will be carbon dioxide. All right. PCl3 will be phosphorus trichloride. So we are using prefixes to mention the number of atoms for the anion, for the second, I'm sorry, not anion, the second element. So phosphorus trichloride. So I'm mentioning I'm mentioning monoxide, dioxide, trioxide. We do not mention mono for the first atom. But if the first first element has more than one atoms, if it is P2Cl5, then I will say diphosphorus pentachloride. So you have to use prefixes to show the number of atoms. On the other hand, if I have to write the formulas, the writing formula is much easier than writing formulas in ionic compounds. So to write formulas, all I'm doing is I will just write what I read. So if I read here is carbon, so it's carbon. Monoxide means one oxygen. Then I read here is carbon, and dioxide means, this is oxide. Dioxide means two oxygens. Then I have phosphorus, and trichloride means 3 chlorines. Then I have diphosphorus, that means P2, and pentachloride means Cl5. So there is no crisscrossing like ionic compounds. You just write as you read. So again, once again, for naming covalent molecules, we are using prefixes to mention the number of atoms. And when we are writing their formulas, we just write as we read. So that talks about naming of covalent compounds. The next thing we want to talk about is Lewis dot diagram. So next topic for covalent compound is Lewis dot diagram. In Lewis dot diagram, we will show the valence electrons as a dot. Okay, we have learned how to do dot diagram for any elements, but here we're talking about all the non-metals. So let's do some Lewis dot diagram of the compounds. So CH4, to do the dot diagram, I will count the valence electrons. I hope you remember how to count the valence electrons. We count the valence electrons by the group number. So So I have group number 1, 2, then 3 to 12. Then we have 13, 14, 15, 16, 17, and 18. So these are this is the periodic table. To get the valence electrons, everybody here has one valence electron, two valence electrons, 3, 4, 5, 6, 7, and 8. So this is how many valence electrons they have. So this number represents valence electrons. So I want to see how many valence electrons I got. So let's get the total first. What is the total I have? I have one carbon atom and 4 hydrogen atoms. So one carbon atom, carbon has 4 valence electrons. 4 multiplied by 1 will be 4. Hydrogen has 1 valence electron. So 1 multiplied by 4 will be 4. I have total of 8 valence electrons. I always divide it by 2 because I'm counting pairs. So count pairs. So how many pairs do I have? I have 4 pairs when I divide by 2. Okay, once I have done my math that how many pairs I have in my hand to do the dot diagram, next step is to choose a central atom. So central atom is something I need to choose. The guidelines to choose the central atom are that you need somebody in there who can play in all corners. Okay, hydrogen will never be the central atom. Hydrogen will never be the central atom because hydrogen has only one electron and it can only play on one side and then it's done, you know. Halogens are usually not the central atoms, although we will learn in this IB chemistry that halogens and even noble gases make compounds. So that will come. But in general, you know, small compounds if you're given, halogen also makes one bond. Carbon, if carbon is there, carbon is always the central atom. Carbon is always central atom. If you have more of the carbons, like multiples of carbons, then they will make carbon-carbon chains. If you have multiples of nitrogen, they will usually make nitrogen-nitrogen chain. So these are the some tips that we need to know. If there is no carbon and there is no indication who is going to be the central atom, then as I said, hydrogen will not be the central atom. Whoever is one element, like if I have PCl3, then whoever is one atom that goes in the center. But hydrogen, even hydrogen is one atom, it will never be in the center. Carbon will always be the center. So let's talk about, so in this situation, carbon goes in central atom. I will arrange my 4 hydrogens in 4 corners. And then I just did the math that I had 4 pairs of bonds that I could make. So I'm going to make 4 bonds right here. And that completes the dot diagram for CH4. Each carbon has 8 electrons around it, 2, 4, 6, 8. Each line represents 2 electrons. So I have 2, 4, 6, and 8 electrons around carbon. Hydrogen is an exception. Okay, octet rule. Hydrogen is an exception to the octet rule. But hydrogen takes only 2 electrons. Okay, boron take maximum of 6 electrons. So we call them incomplete octets. Beryllium takes only 4 electrons. Sulfur takes even more than 8 electrons. So these are exceptions for the dot diagram. But Lewis was the scientist who drew these structures to show the electron domains in the valence shell, and we use this dot diagram to predict the shape of the molecule. So the sharing pair of electrons, each atom has gained electronic configuration, the noble gas configuration here after doing the sharing of electrons as you see here. So let's do some more examples. Let's do an example of NH3. So we do the math again. Nitrogen has 5 valence electrons. You have only one atom of nitrogen. Hydrogen has 1 valence electron, and we have 3 atoms of hydrogen. So, no, it's really 3, I'm sorry. So this is 8 again, divided by 2, 4 pairs. So I have 4 pairs. I'm going to choose a central atom. Of course, hydrogen is not going to be the central atom, so nitrogen becomes my central atom. I have one pair with one hydrogen, another pair with this hydrogen, another pair with this hydrogen. So I use 3 pairs. I'm left with 1 pair. So I'm going to show, because hydrogen doesn't need any more electrons. Hydrogen takes only 2 electrons and hydrogen is happy. So that one pair that is left, I will give it to nitrogen, okay, as a lone pair. And that will complete the octet for nitrogen. It has 8 electrons for nitrogen. So this is called lone pair of electrons. They are free to move. Okay, these are called bonded pair. This is the terminology we will use when we talk about shapes, and how many bonded pairs around the central atom and how many lone pairs around the central atom. So this is how the shape will be discussed for the Lewis dot diagram. So we can also talk about, take some more examples, like let's say CO2. Carbon has 4 valence electrons, 2 oxygens bring in 12 valence electrons, 16. So 16 divided by 2, it will be 8 pairs. Okay. If I told you if carbon is there, carbon is always the central atom. So carbon goes in the center, and carbon makes one bond with one oxygen. There are 2 oxygens. Carbon makes another bond with another oxygen. So carbon has used 2 pairs. Okay, it still has 4 pairs. We still have 4 pairs left. So I want to make sure my central atom has 8 before I do anything else. So I'm going to give 1 and 2 pairs to my carbon to make sure carbon's octet is complete. I used 4 pairs out of 8, and I have 4 more pairs to go. So I will be nice, and I give evenly to both oxygens. So you see that carbon has 8, 2, 4, 6, 8 around central atom on this C, but oxygen has only 6. Okay, so carbon will say, all right, sharing is caring. So based on this rule, carbon will say, okay, let me share one pair with you, and let me share this pair with you. So what we have here is, we have a double bond on this side and a double bond on this side. So you do not decide to begin with, or you do not start with double bonds. You first of all go with single bond, and then whatever is left in terms of pairs, put them as lone pairs, and then see that if you get a stable electronic arrangement. So you do not stop until you have a stable electronic arrangement. And to get a stable electronic arrangement, the octet has to be complete. Everybody must have 8 electrons around them. Let's do some practice of polyatomic ions. So CO3 minus 2. Okay, this is a carbonate ion. Carbonate ion. Carbon has 4 valence electrons. 3 oxygens bring in 18 valence electrons. And then -2 means you gained 2 electrons. I'm going to add that as well. All right, so this is 24 electrons divided by 2. That gives you 12 pairs. 12 pairs. So carbon goes in the center, 1 oxygen, 2 oxygen, 3 oxygen. Okay, it doesn't matter how you draw it. I could draw it like this, so I could draw. We can talk about geometrical shapes later on. So CO3 is what I have. 1 carbon, 3 bonded to 3 oxygen atoms. I have how many pairs left? I used 3. I have 9 more pairs to go. So I'm going to give those 9 pairs to the carbon. I mean, 1 pair goes to the carbon. Maybe it will be better here. So that completes the carbon. I have 3 oxygens on 3 sides. So that I used 4 pairs. 1, 2, 3, 4 pairs. That completes carbon. Okay, carbon has 8. 2, 4, 6, 8. Carbon is done. Carbon is taken care of. But I used 4 pairs out of 12. So 12 minus 4, I still have 8 more pairs. Okay, that I'm going to distribute as valence electrons. So the 8 valence electrons, 8 pairs that I'm left with, I will distribute those 8 pairs to the oxygens. So let's count it together. So I'm going to give it to 1, 2, 3, 4, 5, 6, 7, 8. And you see here that I'm out of all my pairs that I used, I had 8. I'm done. Everybody's happy here. Everybody got 8 except this oxygen. This oxygen is saying I still have 6, and I personally have nothing else in my hand to give it to that oxygen. So then once again the same thing happens that happened before. That carbon will say, okay, well, I have this one sitting here. So I'm going to leave it and give it to oxygen. Okay, let's share it. So at the end, this is what you see, that you have a double bond with one oxygen, okay, and two pairs that it had, and then everybody else had 8, like that. So there is a double bond between one of the oxygen. And then you need to put this in the parentheses and show a -2 charge, because to accomplish this, you added these 2 electrons in there. Okay, so this is how we do the diagram of a polyatomic ion. This also takes us into the topic of resonance. Okay, that's another topic that's called resonance. Resonance means your double bond is going to uh, rotate between the atoms that it's bonded to. So here is one form, all right, and then there is a possibility that that double bond is with this oxygen and not with that oxygen. So that oxygen will take the electrons and the double bond comes here, and then there is a possibility that the double bond is with this oxygen, not these other 2 oxygens. So they have the electrons. The electrons, or the in the bond, are kind of floating. So these are the different variations of the carbonate bond that I could have, in which your double bond is floating and it's not situated at one place. And that so we cannot have a definitive Lewis dot diagram. I cannot say it will always be here or it will always be here. So this thing, it is known as resonance. So resonance refers to a molecule. Okay, resonance refers to a molecule or a polyatomic ion in which 2 or more possible Lewis structures can be drawn. Like right now I drew 3, okay, but not the actual structure. So none of them is the actual structure. Okay, so the actual structure is going to be the intermediate structure of these 3 structures. We can take another example of ozone, O3. So this is how ozone looks like. You have this same thing, okay, and it can be same way. I can rotate that double bond. So I am continuously rotating that double bond. Okay, these are called resonance structure, where the double bond is rotating. So the bond length changes. The bond, you have a bond length here. You have 2 single bonds, and there is one double bond, and double bond is smaller than the 2 single bonds. So you see that the bond length is going to vary as I float this double bond. So the ozone molecule exists as a resonance hybrid. Okay, the resonance hybrid of the 2 or 3 options that you have. I'm sorry, I had all 3. So I have all 3. I don't know what I'm thinking. Um, this and this. So it has kind of a bent shape, okay, that it can be like this. Okay, so this is the ozone, and as I'm saying, it will be the hybrid. The actual structure of ozone will be the hybrid of these structures. So this topic is known as resonance. Let's try another polyatomic ion, that is NH4 plus 1. So nitrogen has 5 valence electrons. 4 hydrogens have 4 valence electrons. Together 9. That positive one means you lost an electron. So I'm going to subtract 1. That makes it 8 divided by 2. It is 4 pairs that we are left with. So nitrogen goes in the center. I have 4 hydrogens right here, 4 hydrogens, and I have 4 pairs. Okay, that takes care of all the hydrogens, but I have to put this in parentheses and put a positive sign here, because to attain this electronic arrangement, I had to lose that electron in there. So that takes care of the topic of resonance. Let's see what these slideshow was telling us. So I'm going to repeat very quickly what we just learned. That we have covalent compounds. Covalent compounds are usually bonded by shared electrons. We can also figure out that how many electrons are going to be shared for each covalent compound. You know, if element is in group 7, which is group 7 of the periodic table, okay, that means it has 7 valence electrons, you know, seven valence electrons. That means it needs only one more to make it 8. Okay, so they will make only one bond. So group 17 at elements make only one bond. Group 16 elements, okay, who have 6 valence electrons, they will make 2 bonds. Okay, so usually they are also the ones who make double bonds. And group 3 elements are going to make 3 bonds, and they are usually the ones who are going to make triple bonds. And group 18 elements will not bond at all because they already have 8 electrons in their octet. Okay, so we can easily figure out which group is going to make how many bonds based on the octet rule. The octet rule is a rule which tells you that the outermost energy level is only stable with 8 electrons. Okay, so this is the most, to get the most stable electronic arrangement, elements tend to have 8 electrons in the outermost ring. So we talked about covalent bonds could be single, double, or triple covalent bonds. We talked about that the triple covalent bond is the strongest bond. It is stronger than the double bond, and it is stronger than the single bond. Okay, in terms of strength and in terms of length, the single bond is the largest bond. Then this double bond is smaller than the single bond, and the triple bond is even smaller than the double bond. So this is in terms of length, and that is in terms of strength. So this is what we learned. Covalent compounds have molecular structure. You know, this is a unit molecule, okay, and that unit molecule will be bonded together in a form to make a giant lattice structure. Okay, and in that giant lattice structure, each molecule is going to be considered as a unit molecule. Then we talked about Lewis dot diagram, how we show electrons around the central atom. So it shows the position of outer shell electrons. Outer shell electrons are called valence electrons in a covalent compound. We have various types to show the dot diagram. We can show as a dot. We can show them all this like this. We can show them as a line. So you see, I can show chlorine has one pair here, one pair here, one pair here, and one pair bonded to another chlorine, another pair here, another pair here, and another pair here. So we can show the pairs by the lines. Okay, the ones that are blue circles. Okay, this one right here. Okay, let me take it blue. So the blue circles, this right here, is the bonding pair of electrons, the ones that are involved in the bond, and the red circles, you know, these are called lone pair of electrons, non-bonding pair, or the lone pair of electrons. This is very important that we understand that what is the difference between the lone pair and the bonding pair of electrons. This is all dot diagram. We learned about dot diagram already. All right. Oh yes, I did not mention the dot diagram of ionic compounds. So we do the lithium has 1 valence electron, fluorine has 7 valence electrons. So when fluorine gains 1 electron from lithium, you know, the lithium is left with only 2 electrons because lithium has a total of 3, and fluorine will show 8 electrons around it because it took 1 from lithium. So we have a negative 1 here and a positive 1 here. So this is how we do the dot diagram of ionic compounds. We can also do the dot diagram of bigger compounds like C2H6. So I told you if you have more than one carbon atom, we make a chain. So carbon-carbon is bonded. Two carbon atoms bring in 8 electrons. 6 hydrogen atoms bring in 6 electrons. Altogether is 14. Divided by 2, I have 7 pairs. So I'm going to put 1 pair right here. And then I have 3 hydrogen atoms on this carbon atom, and 3 hydrogen atoms on this carbon atom, and that takes care of 7 pairs of electrons, okay, for C2H6. Another combination could be N2H4. So 2 nitrogens bring in 14 electrons, 4 hydrogens bring in 4 electrons. That makes it 18 divided by 2. This is 9 pairs. So as I said, if you have more than 1 atoms of nitrogen, I'm going to chain it. So here goes the chain. Then I have 4 hydrogens. So I'm going to have 2 hydrogens on one nitrogen atom and 2 hydrogens on the other nitrogen atom. Okay, I have 1, 2, 3, 4, 5 pairs I have used already. Okay, I'm left with 4 pairs. So I'm left with 4 pairs, and for those 4 pairs I will make it a double bond. Okay, I did a, see, I'm not in the right. It should be 7 pairs. So 1, 2, 3, 4, 5, 6. 6 I already have. 10 and 4 is 14 divided by 2, it will be 7 pairs. Yes. 2, 4, 6, 8. 2, 4, 6, 8. Alright. And you have another pair as a dot. I was okay. I know what I'm saying. I'm doing a wrong formula. N2H4. So N2H2. 2 nitrogens. 2 times 5 is 10. And 2 hydrogens bring in 2. That is 6 pairs. Now it makes sense. So 1 pair. And then I have 2 hydrogens. So 2 here. 2 hydrogens. So I use 3 pairs out of 6. Okay, I put 3 pairs like this, you know, but this nitrogen does not have 8, so I'm gonna give this 8. So 2, 4, 6, 8, 2, 4, 6, 8, and I used my 6 pairs. So this is how it goes. All right, you need to practice the dot diagram for these compounds. All right, the next thing left is the coordinate covalent bond. The coordinate covalent bond is also called dative bond. Okay, so some molecules, some atoms and molecules, both, okay, it can be atoms or molecules, that will contribute both electrons in a covalent bond. Usually what happens is that one electron is shared by one element and another electron is shared by other atom or other element, and they share it, so they're equal contribution. But there is a possibility that both electrons will be contributed or donated by one atom. So for example, if you have H2O and you give another proton to it, you know, proton means it is left with, it has no electrons, 0 electrons in only, because hydrogen is 1 1, you have 1 proton and 1 electron in the actual hydrogen atom. So when that hydrogen is +1, it means it has lost that electron. So this hydrogen does not have any electrons at all. If I look at the dot diagram of water, this is how the dot diagram of water looks like. Okay, it has 2 valence electrons. So this is what the dot diagram of water is. If I add another hydrogen ion to it, so oxygen will say, okay, I'm going to share a pair with you. Okay, so I have a hydrogen and hydrogen right here, and I'm going to share my whole pair with you, and usually we show it as an arrow. Okay, so we show as an arrow that oxygen is sharing both of its electrons with hydrogen, and that gives oxygen a positive ion. Okay, so this kind of bond, this bond is called dative bond. This bond is called covalent bond. You know, this is a single covalent bond. But this bond where both electrons are donated by one atom is called the dative bond. So in this example, the lone pair from the water molecule has formed a dative bond to a hydrogen ion. Okay, let's take more examples of dative bonds. I have ammonia here, NH3, and nitrogen has two lone pairs right here. BH3, boron is an exception. Boron makes only 6 bonds. So boron doesn't have anything. But nitrogen can say that I can give you both of my electrons to make a bond. So nitrogen will share both of electrons, both of the lone pairs with boron to make this dative bond. So dative bond, as I said again, is also called coordinate covalent bond. Coordinate covalent bond or dative bond is the same thing. So these are the different examples of dative bonds. Then next thing left is called expanded octet. I talked about that some elements like sulfur is an exception to it. It takes more than, it can hold more than 8 electrons, and to do that it uses its 3d orbitals, the d orbitals. So these are called expanded octets. Period 2 elements cannot do this because they have no d orbitals. So this thing happens beyond period 3. Okay, it does not happen for period 2 elements. So where sulfur can use its lone pairs and its d orbitals to make expanded octet. The next thing we want to talk about is more practice of doing dot diagram. Al2, Cl6, XCF4. You see here is a noble gas who's making dot, bonds. So we learned about naming already. We learned about polarity already, and that we learned about resonance, and that is it. So what did we learn in this video? That atoms generally form covalent bonds according to the octet rule. Okay, nonmetals and nonmetals are the ones who make covalent bonds. Each covalent bond gives an atom an extra electron. In the dative bond, both electrons in the bond come from the same atom. Period 3 and above elements can break the octet rule by using the empty d orbitals and might have 12 or more electrons in their outer shell. So that takes care of the discussion on covalent bonding, and we will discuss the rest in the class. Thank you. Bye-bye.